So we're going to learn Coulomb's law today. Oops. Every time. Coulomb's law. So, I'm just going to say recall. We learned Newton's law of universal gravitation looked like this. Okay. And from this, we figured out that the force of gravity is proportional to m and m, the product of m's, and inversely proportional to the square of r. All right? This, which we call the universal gravitational constant, came later. It was found out by Cavendish many years after Newton came up with the original relationships. Okay? So why am I mentioning this? Well, it turns out that you can look at electrostatic attraction in sort of a similar way, or repulsion, really. And so let's say that we have two charges. A and B. Okay. And let's say this is like, I don't know, say this is 1 times 10 to the negative 5 coulombs, and it's positive. Let's say this is 1 times 10 to the negative, let's make this 2. 2 times 10 to the negative 5 coulombs. We'll also make that positive. Okay, so first question, will these repel or attract? They will repel. Okay. Now through experimentation, scientist named Coulomb came up with a relationship that showed a few interesting things. And let's just put an R in here. Okay, so this is the distance between the two objects. And he found a few things that will look familiar. The force of repulsion or attraction is proportional to the product of the size of the charges. So Q and Q, right? Oops, that looks more like a G than a Q. There. Okay. And he also found this. Okay. So, a very similar result to gravity, to Newton's law of gravity, all right? Just think about it, it probably maybe sort of makes sense, right? As you increase the charge, it would make sense that the force would increase linearly. I don't know if that makes sense, but it does. And then as you increase the distance between the charges, the force decreases, but at a square to the distances. And we'll talk about why that makes sense in just a second. But from this, Coulomb's law was created. Okay, where K is called Coulomb's constant. Q and Q, these are the sizes of the two charges involved in coulombs. And R is the distance between the charges in meters. And F is the electrostatic force between the two objects. So that is going to be measured in newtons. So here's a quick and fun question. What units do you expect K to be in? Okay, so we need the value for K, for Coulomb's constant. And that looks like this. 8.99 times 10 to the 9. Notice it's much larger than the gravitational constant, much order of magnitude is much larger. Then Q, so we must be in terms of newtons, right? Because we got to end in newtons. We must have coulombs to the power of -2, right? Because they have to cancel the 2 coulombs off of here. And meters squared, because you're going to have 2 meters on the bottom multiplied together. and they're going to get divided into. So this is Coulomb's constant. Yeah, oftentimes people just leave it like this. Okay? So there you go. There's Coulomb's constant. And now you'd use it just as if, as if it were any other formula that you have in your bank. Should we do an example with it? Sure. Well, let's solve this one. Let's say these guys are like 30 centimeters apart. Okay. So they're 30 centimeters apart. Let's see if we can solve for the force between them. Okay. So K QQ over R squared, so K 8.99 times 10 to the 9 times 1 times 10 to the negative 5 coulombs times 2 times 10 to the negative 5 coulombs, all over 0.30 meters squared. So I get 20, and that, just to confirm, is totally by fluke. I just made these numbers up. Yeah, nice 20. Nice round number. Okay, so 20 newtons. And that is basically how you go about using that formula. Okay, let's extend this a little bit. So you might see a problem like this. I'm not going to go too deeply into how to solve it. Because we've sort of dealt with stuff like this before. But what you might see is, you might see something where you have some charges and they might be like arranged, say, like this. Let's move them so they're in a nice shape here. Okay, I think last time we mentioned that if you have a positive charge, the field lines are drawn away from the charge, right? If they're negative, they're drawn into the charge. So what we might have is something like this set up. These would have values on them. And if they're named, like let's say A, B, C, and it says, you might have a problem that says find the net charge on B. Essentially how you do that is you just look at the two separate forces acting on it. So imagine that A and C are fixed in space. You're gonna do AB first, right? So the electric force between A and B would look like, this. And it would be attractive, so this would be a leftward force. That would act like in this direction. Okay, and then you'd also have for BC, you'd have FE again, KQQ over R squared, and that would act in this direction. So then exactly like you would now that you have forces, you just add the two force vectors together, right? So you have a force vector that way and a force vector that way. So essentially, exactly, and then you find the angle, right? But if you look at it, it kind of makes sense, right? It's getting pulled this way, and it's getting pulled this way. So combine that together, and it's going to tend to move over this way, right? If you look at the way, yeah, don't worry about that, actually, sorry. Just imagine it's being pulled to the left and down at the same time. It's going to move off into this direction. So this is just like a two-step problem. First, find the two forces that you need to deal with, and then sum them like we've done 1,000 times with other forces. Any questions about that? Okay, just realized I wasn't recording there for a little while. Whoopsies. So just an explanation of what we talked about. Okay, so imagine you have a collection of positive charge. This is for the benefit of people that are not here right now. And we know from last class that the way you draw that field is you imagine there's a positive test charge and you put it in the space around this. So in that case, you're always going to have field arrows pointing out. Now let's say we're interested at some specific point in that field, okay? One way to describe it was that the electric field strength is equal to F over Q, or newtons per coulomb. So however much force some amount of charge feels here, okay, is its field strength in terms of newtons per coulomb. And we also put a little by the way that sometimes the field strength symbol is a curly E rather than an E. So if you see it as a curly E, don't be alarmed. It means the exact same thing. If we then take this formula and we say the electric force is equal to whatever charge we have times the strength of the field, okay? This is an equation that tells us the amount of force some charge Q would feel if we knew the field strength, okay? But we also just learned from Coulomb's law that another way to talk about the forces would feel is equal to KQ over R squared. What this does is it gives us an opportunity to make QE, right, this FE, equal to this FE here. The little q cancels off, and what we're left is with a formula to calculate the strength of a field somewhere near a collection of charge. If we know how much charge is there, we'll now have a formula that if we know a distance away, we can find the field strength. So in this case, we have 15 centimeters away. And let's give this a value. Like let's say this is 5 millicoulombs. Okay, we'll say it's 5 millicoulombs. So what field strength do we have 15 centimeters away from a 5 millicoulomb charge? This is the thing that this allows us to answer. So what do we get? We get K, we get Q over R squared. Very useful formula. So 9.0 times 10 to the 9 times Q, we said that's 5 times 10 to the negative 3 coulombs. I think I said millicoulombs. Yes, I did. And we are 15 centimeters away. Do you think it's going to be a large or a small amount of charge? Or sorry, field strength. Okay, so this gives you a very massive value. Okay, so you get 2 times 10 to the 9 newtons per coulomb. Okay? Okay, so last thing I want to talk about is the combination of electric fields together. Okay? So let's imagine that we have this setup right here. Let's say this is 3 times 10 to the negative 6 coulombs, and it's positive. Let's say this guy is like I don't know, like 1.8 times 10 to this negative 6 coulombs, and it's negative. So the first thing I want to do is I want to imagine what the force field here would look like. What does the electric field look like? Well, it's blowing out a positive, right? If you think of it like a wind, I told you to do, it's blowing out a positive. So you'd have this, right? You'd have some of this action, right? Stuff like this, and so on. So we can use the formula we just had to actually figure out exactly what the field would look like really at any point in space. Okay? So I'm just going to quickly erase this stuff out of here, and we're going to solve a little problem with field strengths. Okay? So let's imagine that right here, okay, right here, we'll say this is 30 centimeters away from here, and we'll say it's 105 centimeters away from here. Okay, that little star in space. You might be asked, hey, what is the field strength at the little star? Field strength. Okay, so basically, okay. Sorry, a couple of weird interruptions there. Okay, so this is how we're going to look at this. We imagine that flowing out of the positive, right, we have a field directed down and in this direction, okay? And we also have flowing up and in a negative field. So at the end, what we'll have, right, is we'll have the combination of this field plus this field. There's a little bit of work to do here. We learned this, right? This, again, is not a charged object. What we're trying to do is figure out what direction and size the field will be here, so that if we placed a charge here, we would know what direction it would tend to go in, right? So E, K, Q, over R squared, okay? So we can figure that out. So the first thing we need is we need this angle right here, okay? Wow. Okay, so to figure this out, what we need to do is we say theta is equal to the inverse sine of opposite over adjacent. And so that gives you 16.6 degrees. 16.6 degrees. Okay, so we know the field coming out of here is directed at 16.6 degrees below the horizon, and it's down and to the right, okay? We also know there's a field directed up and in here, so what we're going to have to do is add those two fields together. So let's figure out what they are first. So I'm going to just label these to help me remember. Call this A and this B. So we'll go E from A is going to be equal to K, so 9 times 10 to the 9. Just for speed, I'm going to leave off the units. You really should put the units in there, but we're in a time crunch here. Everything has to be in terms of meters. Make sure you do those conversions. And we'll 2.45 times 10 to the 4 newtons per Coulomb. And that's 16.6 degrees below horizon. So we'll need that later. And let's do B. Notice I don't include my negatives and positives. That is not necessary. They're just vectors basically saying a direction. So I'm going to make sure that when I write them out, I say which direction they're going in. But I do not have to put negatives or positives into my formulas. 1.8 times 10 to the 5, and that is up. Or if you want, north, right? But obviously, think of it as northeast, south, and west. That's fine too. Okay, so now to get the overall net field here, we've got to add these two things together. These are both vector values, right? Fields have a direction. So we add them as we would add any vectors. So basically it's this. It's 2.45 times 10 to the 4 newtons per Coulomb plus, oh, sorry, I forgot the direction. That's key. Key info. 16.6 degrees. You know, I might actually just change it to directional help, south of east. Okay, plus 1.8 times 10 to the 5 newtons up. Okay, so let's draw that. So we've got the 1.8 times 10 to the 5. Like that. We've got this guy kind of like this over here. And our resultant field is going to be off in this direction. Okay, so somewhere up and to the right. Does that make sense? Heck yeah, because our field lines are going to come like this, right? Come here, like this, and like that. So that makes perfect sense. So we have to use our old method of vector components to solve this. Okay, so let's do it as quick as we can. So we've got this guy here. Right, this is our field here, so we need to break it into its components. Okay, 2.45 times 10 to the 4 is there. This is 16.6 degrees south like that. So this should be the cos, so it should be 2.45 times 10 to the 4 cos 16.6 equals the field strength in the x direction. Okay, this should be ringing a bell, very similar to what we had to do before. 2.45 times 10 to the 4 times the sine, because now we're dealing with the opposite one, 16.6 degrees. And this is in the southerly direction, and this is in the easterly direction. And let's get numbers. Okay, so for this guy here, I'm getting 2.35 times 10 to the 4 east. And then here you get about 7,000 to the south. Okay, perfect. And now we have everything that we need. Okay? So now what we're going to do is we're going to go our x net, right? We're just going to be able to, like, the x on here plus the other x which does not exist. So x net is just this value in the easterly direction. And then we need y net. So we have our 1.8 times 10 to the 5 newtons up, plus this is to the south, so negative 7 times 10 to the 3. Okay, so this will end up being overall in the northerly direction. So we get 1.7 times 10 to the 5 north. And remember the units here, guys, the units are newtons per coulomb, right? Because we're finding out about a field. Okay, and then last but not least, we just need to do our final solution here. 2.35 times 10 to the 4 east plus 1.7 times 10 to the 5 north. And the solution to this will be the final answer to the problem. So that's what we're after in terms of our field strength, just like we suspected. So do Pythagorean theorem here, find an angle, and we're done. 1.7 times 10 to the 5 newtons per coulomb. And then the angle should be equal to, theta should be equal to, why doesn't it want to write here? The inverse tan of that over that. Oh yeah, sorry. You know what? You're right. I rounded too much. So that's not appearing in there. Let me just fix that. It's actually 1.72. Sorry. It's a pretty insignificant value, right? This is going to be a very large angle. So the actual difference between these two is going to be pretty low. This is, remember, this is a whole order of magnitude smaller. It's like 10 to 1, right? So that's why you get that kind of scenario going on. So you get a theta of a large theta angle of 82 degrees. Okay, so what do we mean by that? All we mean, right, all we mean is that at this point in space, right, we're off here, up in this direction in terms of our field. That's exactly what we would expect, right, since our field is kind of going like this. Okay, so that's a way to figure out what our field would look like in that position, okay? So it's kind of a lot of work to do. If you're very ambitious, you could look at all the places around these two charges and figure out exactly what angle that field's acting at that position. But basically, it's just applying some stuff that you've done before. And here's your final answer, right? 1.72 times 10 to the 5 newtons per coulomb. I should say 82 degrees north of east, or you could say 8 degrees east of north. And we're done.